Hello, I'm Vanessa Bartley, Project Manager and Mechanical Engineer of Team 31. In this mission, the probe will land on one of Saturn's moons, Titan, to identify hydrocarbons present in Kraken Mare. The data collected will help our understanding of how Earth and other celestial bodies have formed. The mission concept was kept simple and has one main focus. Having a simpler mission required less instrumentation and less chances of a failed mission. Adding additional instruments and experiments may have affected the strength of data transmission, vehicle size, and budget. The probe will deploy from a Titan orbiter spacecraft, descending into Titan's atmosphere, and will land in one of the mares to study the elements. As the orbiter spacecraft is above the northern pole, the probe will be released and descend toward the middle of the target, Kraken Mare. Upon being released and having descended 20 meters using the laser altimeter, 2 parachutes will deploy from the top of the probe. Soon after, the landing system will stabilize the fall into the Kraken Mare by using hydrogen tanks, which will also keep the probe afloat. Once landed, the instruments will engage in its surroundings and collect data. The probe design changed a few times. The first design we came up with was spherical with a robotic arm. The robotic arm had a full range of motion, allowing data to be collected inside the lake and along the edges. However, we felt this didn't fit the science objective that we wanted to attain. This led us to our next design, which was a submarine. The science objectives could expand, however, it came with more challenges. One of the main cons of the submarine was the aerodynamics of the oblong shape descending into the lake after detaching from the orbiter. A minor accident from descent or manufacturing error would result in a failed mission if liquid got inside the probe. The final design of the body of the probe resembles a capsule that astronauts use when heading back to Earth. The pros of the design is its aerodynamic, and the shape has been tested and used numerous times. The shape allowed for a heat shield to easily attach to the bottom, covering the hydrogen tanks. There are 8 hydrogen tanks used for stability. With the ability to float, the antenna would have better communication with Earth versus a signal from underneath the liquid. The cons to the design is navigation is non-existent. The reason navigation wasn't selected was due to the science experiment being attainable without the need for navigation. Now I'll take it over to Oscar, who will go over the design more in detail.
Hello, everyone from the Space Team. My name is Oscar Venegas, systems engineer and designer of our probe. So right here, this is a probe chassis and shields. The outer probe's environment is in a protective atmospheric shell. The shell has 2 parts. It has this top shield and this bottom shield. This top shield with parachute P1, and the front shield, which is down here, the atmospheric front shield, is made of titanium with a thin gold and platinum outer protective shell for atmospheric entry. So that's just the basic understanding of the shield. They'll protect the probe. And the probe's body, here we go. The probe's body is comprised of several different sections for payload and subsystems. The base of the probe, which is down here, is about 5.1 meters in diameter. There are 8 hydrogen tanks right here, right below it. 8 tanks right below the probe to help it flow on Kraken Mare. They are 0.79 meters in diameter each tank. Also located at the base are 2 coupler housing with the altimeters intact for stability. The FTIR spectrometer with the glass vacuum tube system will be connected to each other with brackets and coupler housings for the test tubes. The test tubes are released into the surface of the lake and reeled back by servo motors and into the spectrometer. The nitrogen engine systems are stationed on a motor mount with 2 nitrogen tanks in the middle, reinforced with brackets to hold the tanks. Motors are fed via hoses and couplings to restrain. The Master Z camera, which is right here, is stationed in the top middle on an elevating platform, which is right below right there. The camera will elevate once it has reached full stability, no shimmy. Antennas are located right here where it says antenna. At the very top to transfer data without interference to the orbiter and from the orbiter to the deep space network. So there you go. Thank you. And I will now pass it down to Samantha Garner.
Hello, NASA and Low Space Academy. My name is Samantha Garner. I am the astrophysicist on Team 31. The way we're going to be performing the tests with the probe is through the use of multiple instruments. The first few are going to be the laser altimeter, the parachute system. So what those two are going to do is scan around the moon and determine where the Kraken Mare is. Once it finds the proper location, it'll drop the probe. And using the parachute system, it'll determine at what altitudes above the lake the parachutes will deploy in order for it to drop into the lake at a safe velocity without doing any sort of harm to the probe or destroying the heat shield or anything like that. Once the probe hits the lakes, it'll have hydrogen tanks on the bottom that will begin to let the probe submerge a little bit into the water or into the lake. Once the probe is partially submerged into the lake, there will be a little door at the bottom of the probe that'll open up. That is where the opening of the test tube is going to be. Back on Earth, it will be a vacuum inside of the test tube, so as soon as the door opens up, it'll begin to suck up the lake. Once that happens, the spectrometer will start scanning the sample for all the hydrocarbons that the lake is essentially made out of. And then while this is all going on, there will be a camera that is mounted essentially kind of on a mast on the probe. It'll be scanning the surrounding areas around the Kraken Mare to give us a little bit better imaging of what the lake should look like and the areas around the lake. The way we plan on paying for this is over the course of 6 years. We hopefully will be employing multiple scientists and engineers and interns. So hopefully if we get enough interns, we'd be able to use their facilities if they're all around in the same area, meaning we can use their colleges or universities, wherever they are, to build their probes and kind of help give them an insight of what they can expect to be doing in their futures. The total at the end of the 6 years would be around 330 million. So we were well within our 350 million budget. Thank you, and I will pass this on to Lauren.
Hi everyone, my name is Lauren Stoops. I'm going to be going over the orbiter system as well as the orbiter and probe communication. So we're going to start off with the orbiter. So the orbiter is going to have a main satellite, and this is going to be a high gain satellite, and then we have 2 low gain satellites. And these 2 low gain satellites are going to communicate with the probe. And so this orbiter is going to remain tightly locked to the sun, and the reason why that is because this main satellite is going to act as a shield from the sun to protect the payload of the orbiter. And then on the back of the orbiter, there are 2 ion thrusters, and we'll get into that on the next slide. So next slide, we have our nitrogen ion thruster. This thruster is going to be nitrogen powered. So I have 2 separate things. We got powered by an RTG battery. Ammonia is created by hydrogen and this pressurized nitrogen gas. Everything's going to be in steel tanks. It's going to go through a pressurized container. A sheet of iron is going to be heated up with the RTG battery, create the environment to create ammonia. And that ammonia is going to be traveling through the entire orbiter to act as a system. It's going to keep everything temperature-wise stabilized. And then we have our nitrogen thruster. So this nitrogen gas in the other tank is going to be pressurized and released into our nitrogen ion thrusters. And what this is going to do is we have 2 sources of heat and one of a lower temperature. And this difference is going to cause the magnetic lines on both sides of the thrusters to ionize that nitrogen gas and be able to propel the orbiter. And then we have our communication system. So on top of the probe is going to be 2 antennas. Everything that's gathered within the probe, including information and everything we find, is going to be relayed back up to the orbiter. This will be orbiting Titan, and absorbed through those 2 low gain satellites. These low gain satellites are going to transmit that information to the main satellite up front, which will be relayed back to Earth.